Hello and welcome to another episode of Cloudcraft. I am your host, George. Now, if you have been working in the cloud for more than an hour, you have likely heard the pitch. Just deploy across multiple availability zones and you are golden. It sounds simple, doesn't it? Like a set it and forget it recipe for reliability. But here's the thing, and it is a bit of a spicy take. Standard multi-AC steps are often only good at catching the big stuff. We are talking about the everything is on fire scenarios, like a major power cut or a literal earthquake hitting a data center. AWS is brilliant at handling those binary failures, where a resource is either 100% up or 100% down. But what happens when the things get messy? What happens when a network link is just a bit flaky? Or a database is only rejecting connections from one of specific corner of your architecture? These aren't binary failures. These are what we call gray failures. And honestly, they are the stuff of nightmares for site reliability engineers. Today on Cloudcraft, we are going to deep into the advanced multi-AC resilience patterns. We are moving beyond the basics. We are going to talk about how to spot these snaky gray failures, how to use a bit of statics to find the signal in the noise, and to build a big red button that lets you evacuate an entire availability zone without breaking a sweat. So, kettle on, settle in, and let's get into the nitty gritty of cloud resilience. Right then, let's start with the villain of our story, the gray failure. In a perfect world, if a service fails, it tells you. It's throw a 500 error code. Its health check fails, and your load balancer neatly sidestep it. But a gray failure is subtle. It is defined by something called differential observability. This is a fancy way of saying that different parts of your system see different things. Imagine you have got three apps, app 1, 2, and 3, all talking to a database. The database thinks it's fine. Its heartbeat is steady. Its CPU is low. It says I am healthy. But app 1 is having a nightmare. It's seeing a massive spike in latency, maybe 70 milliseconds instead of as usual 50. Meanwhile, apps 2 and 3 are chugging along quite happily. From the database perspective, the average latency hasn't crossed an alarm threshold, so it doesn't trigger any recovery. But for app 1, the system is essentially broken. That's a gray failure. The system thinks it is healthy, but the workload knows it is unhealthy. In an AWS context, happens in the availability zone level. You might have a networking glitch specifically between AC1 and AC2. Your instance in AC1 can talk to the Aurora database in AC2, but the database itself is perfectly fine and happily serving instance in AC2 and AC3 because the database and the load balancers still pass their own health check. The standard automation does absolutely nothing. You are stuck in the gray zone, and your customers are feeling the pinch while your dashboards are stubbornly green. So the question is, how do we fight something we can't see? The answer is high-fidelity multi-AC observability. You can't just rely on the standard CPU usage or disk IO metrics that come out of the box. You need to instrument your code to tell you exactly what the customer is experiencing. And crucially, you need to know which AC that experience is happening in. This means Every metric you emit needs dimension. At a minimum, you want the region, the ACID, and the specific action or controller being hit. The quick tip here: always use the ACID like ES1-AC1 rather than the AC name like ES East 1A. Why? Because AC names are mapped differently for every AWS account. But the ACID is physically consistent across the whole AWS. Now, once you got these zonal metrics, you can't just stare at 100 different graphs. You need CloudWatch composite alarm. These are brilliant. They let you create a hierarchy of logic. You might have a successful rate alarm for each AC, but you don't want a single flaky server to trigger a massive failover. So, you use contributor insight to check if the errors are coming from just one or two bad apples, or if they are spread across the whole zone. Your final alarm only fires if three things are true. The first, success rates are down in AC1. Right? Success rates are fine in AC2 and AC3. So we know it is not a regional issue. The third one is the errors are coming from a significant percentage of your instance, not just one lemon in the fleet. This gives you a clear automated signal that says something is wrong specifically with AC1, and it's big enough what we need to act. Now, sometimes even composite alarms aren't enough. What if you have a noisy environment? Take AWS Lambda for example. You always get a few errors here and there. Maybe a developer forget a dependency in a zip file, or there is a timeout. If you see hundreds errors across your whole fleet, is that just normal noise? Or is one AC actually failing? This is where we get a bit clever with statics using outlier detection. One of the best patterns mentioned in the sources is the she-squad test. Stay with me, it is not as scary as it sounds. Essentially, you start with a null hypothesis. The assumption that errors should be evenly spread across all your ACs. If you have hundreds errors and 4 ACs, you would expect about 25 errors in each. The cheese squad test looks at the actual distribution. If AC4 has 35 errors and the others have 20, is that just bad luck? Or is statistically significant? If the probability of that happening by chance is less than 5%, you reject the null hypothesis. You have found your outlier. The beauty of this is that it detects an AC impairment even if you are seeing errors everywhere. It identifies that one zone is behaving differently from the others. You can run this logic in a lambda function every minute, and if it spots a statically significant skew, it flips a bit that triggers your composite alarm. It is like having a digital detective constantly looking for patterns that a human eye would miss. It is like having a digital detective constantly looking for patterns that a human eye would miss. We have talked about detection, but the detection is useless if your architecture is so tangled that you can't isolate the problem. This brings us to availability zone independence or ACI. The goal of ACI is to make sure that a failure in one zone doesn't bleed into the others. A classic mistake is cross-load balance. It's often turned on by default because it keeps your traffic even, but in resilience scenario, it's a liability. If AC1 is flaky and your load balancer is happily sending 33% of AC2's traffic over to AC1, you have just spread the failure. Turn it off keep the traffic within the zone. The real boss level of AC1 is the database. Most relational databases have one primary writer in one AC. If that AC goes down, the whole system feels it. For your read traffic, you should use zonal read replicas. Don't just use the generic reader endpoint that load balances across the whole region. Instead, give each its own specific replica. Your app in AC1 should only ever talk to the replica in AC1. This way, if AC3 goes into a meltdown, AC1 and AC2 can keep on reading and writing as if nothing happened. You have effectively firewalled your zones from each other. Right, final structure. You have detected a gray failure in AC1. Your architecture is independent. Now, you need to get out. You need to evacuate. There are two ways to do this, the data plane and the control plane. Think of the control plane as the administration of the cloud, changing configuration, launching new instance, updating ASGs, etc. During a major event, control planes can be a bit slow or even impaired themselves. The data plane, however, is the doing part, routing packets, serving requests, and so on. Data planes are built to a incredibly simple and rock solid. When you need to evacuate, go for the data plane first. The absolute gold standard here is Amazon Route 53 Application Recovery Control ARC zonal shift. With one API call, you tell AWS stop sending traffic to AC1 for this load balancer. It happens almost instantly at the DNS level. If you want to be even more crafty, you can build a self-managed HTTP endpoint. Your instance can periodically check a health file in an S3 bucket or a DynamoDB table. If you see a circuit breaker flag on their AC, they can intentionally fail their own health check. This tells that load balancer to stop sending them work without you ever having to touch the AWS control plane. Once the bleeding has stopped and your traffic is safely in the healthy zones, then you can use the control plane to clean things up. You can update your auto-scaling groups to remove the subnets in the bad AC, ensuring that no new instances are launched into the fire. We have covered a lot of ground today, from the subtle differential observability of gray failures to the statistical rigor of G-squared outlier detection, and finally to the andant codes of zonal shift. If there is one thing I want you to take away from this episode of Cloudcraft, it is this. Resilience is not an accident, it is an investment. Building these advanced patterns takes real engineering time. You have to write the instrumentation, you have to build the big red button, and most importantly, you have to test it. But for this mission critical app, it is worth it. It is often cheaper and faster than building a complex multi-region setup. And it can give you a much better recovery time objective. You are not just hoping the cloud stays up, you are masterminding your own survival. Thanks for joining me on Cloudcraft. I am George and I will catch you in the next one. Stay resilient, everyone. Thank you.